Chapter 8, Section 2, this is the second part of Section 2, which is the elimination method. We're working with systems of equations, and specifically we're going to work with two equations. And when we have a system, again, we're trying to find a ordered pair or a relationship between the variables that will work with both equations. And we've talked about a couple things. When you have, again, these are linear, so if you graph one of these, that's what they started with. They're going to show graphs basically for visualization method, and really what the first section was about was really just how do I kind of get a picture of what's going on with these systems, because it's real critical, because it's there's a lot of steps, a lot of process. It's very easy to forget what you're really trying to pull out of this situation, which is a solution to both equations. So like in this case, this visualization they're going to give us for elimination. You know, if I graph these two lines, where this intersection point is an ordered pair, an x and a y value that works for both of these equations. Okay, so that's kind of a little bit of review of that again. And then we went through substitution, which we do a lot of in substitution. It gets a little bit different when we're talking about substituting a variable with another algebraic expression with a variable in it. And that's, once you get past that idea that you can do that, then it's pretty much the same process that we go through. And strategy-wise, why are we doing this when we have two equations with two of the same variables? The point is to try to create an equation that has one variable. When I have an equation with one variable, I can solve that equation and I can get an actual numeric value for that one variable. In other words, then I have part of my solution to the system, or part of the common ordered pair. Like in this case, if I found the x value, which will be a fractional number, which is pretty hard to grab, or you'd have to just guess on this from this graphing. But when I get an actual x value, I can plug that x value into, or then I'm going back to substitution, I can substitute the number for the x value in either one of these equations, and now I have an equation with one variable again. So I can solve for the other variable and find out what is the other part of my ordered pair. Now sometimes I might get the x value first, and sometimes I might get the y value first. But so you'll see both things happen. Well, we did substitution was a way to create an equation with one variable. Now we're going to use the addition principle to take kind of this next concept leap, or whatever it is, that which is the addition principle, says I can take any equation and I can add the same thing to both sides, and I end up with an equivalent equation, or equation with the same solutions. So we're going to do that when I have two equations, and we're going to do it with a purpose in mind, is that we want to be able to add these things together so one of my variables will go to 0, and when I get 0 times that, I end up with 0 of it, and then we have that 0 principle of addition and things like that we've defined back in chapter 1, which means that I end up with an equation with one variable. So keep that in mind. This is going to be I see with a lot of students that first you do need to attempt. I mean, homework is real crucial in the sense that you need to attempt. Maybe sometimes you'll fail, or you'll basically have to see if you have all the pieces together, and maybe you have the pieces, but you get lost in which order to go on, those kind of things, or you forget where you're going, and that's usually what I see. But you need to attempt, and a lot of times after you do a few of these, you're going to say, oh, I get how this works, and sometimes this is the best method. Actually, substitution and elimination, depending on what you start with, you're going to make some decisions about which method you're going to use. Depends on what the equations look like when you start. So it's a strategy, really. Again, what's a problem-solving strategy? So example 4, it says solve the system. We have 2x minus 3y equals 0, and then because there is, we're going to do things with multiple equations, they name this equation 1, just so when they're referencing it, they don't necessarily have to write it all out every time. They're going to say which one are they talking about here, which equation. So this one is equation 1, and this negative 4x plus 3y equals negative 1 is equation 2. So let's go about how they describe what they're going to do here. It says according to the equation 2, which is that second one up there, negative 4x plus 3y and negative 1 are the same number. Now, why they're referring to them as being a number is they're trying to refer back to this addition principle. But another way to say it is that they are equal, and you'd say, well, yeah, I can see that. I mean, that's an equation. But they're kind of referring to this with a little bit different languages. What it means that this side is equal to this side. So for addition principles, if I add this to one side of something and I add this to the other side, I am virtually adding the same values to both sides. It'd be kind of like if I had a balance scale again, and I had this one weight that was 10, and then I had this weight I didn't know the value of it, and this other weight that was different. I'd say, well, that's x and this is y. It'd be like saying x plus y equals 10. Well, if I wanted to add 10 to one side, could I take the x and y weights and put them together and put them on another scale and know that I've added 10 pounds? Well, yeah, because it balanced with that weight that I knew was 10 pounds. So that visualization and getting that in your mind. So what we can use the addition principle by adding basically equations together. And that's what they're showing here. They're showing up and down addition. Is that 2x minus 3y equals 0 is equation 1. Here's the second equation. And what they're doing is up and down addition here. It's kind of like I can add this. But if you think about it, I'm adding this to this side, and I'm adding this to this side. I'm actually adding an equivalent thing to both sides of this, so I can use the addition principle. Now the name they use is elimination, which is, I think, a really good name because it reminds you, what are you trying to do? I'm trying to get one of these variables to go to 0 times it. In other words, I'm looking for additive inverses because additive inverses add up to 0. Well, in this case, hey, the y's here, this is really plus a negative 3y, and this is plus 3y. Well, negative 3y and 3y are additive inverses of each other. If I add these two things together, I get 0. I have basically found a way to eliminate the y variable in an equation, so I end up with one variable. And I end up with this. I still have to add the rest of it. Here I have 2x plus negative 4x is negative 2x. Plus I have to do the addition on the other side. But on this side, to represent this expression, we have a number. We just go 0 plus negative 1 is negative 1. The resulting equation is this one. It is one that I can solve and get an actual number for one of my variables. Negative 2x equals negative 1, so x equals 1/2. If you put 0.5 here because you still think you need to do division, I would be concerned. We're going to be dealing with fractions a lot, and the way the answers are going to be expected to be is in fractional form. So be careful. I know it seems easier, but in a lot of ways, like when we were dealing with slope-intercept form, it's hard to get to the right form to be able to get out what the slope actually is and your y-intercept if you have a bunch of decimals in there. So with that said, okay, so I would hope that you take negative 1/2 times both sides, which is the reciprocal of negative 2 is a negative 1/2, and I end up with a positive 1/2 for x. So what do I have here now? I have a number for one of my variables that should be the common solution, or the solution to the system, which is going to be an ordered pair. Well, I know what my x value is. Well, now we're back to substitution. Is that if I know the x value, I can put that into either one of my equations. And they use equation 1 in this case, which is 2x minus 3y equals 0. Well, they put 1/2 in for x, and you get minus that multiplication minus 3y equals 0. Hey, now I have an equation with just y in it. I can solve for y, and I'm going to get my other part of my ordered pair. So, and we solve this and we get a positive 1/3. So I have an ordered pair. Now, they show us the graph for a visualization, and which is good. I like to look at these sometimes, or get some kind of general idea what the graph is, because if they don't intersect, I have some other things that could occur, and we'll talk about that again a little bit too. But now I have an ordered pair I think is a solution to the system, which means, what does that really mean? It's a solution to both equations. So I check that. So you put the ordered pair 1/2, 1/3 in, so you put it 1/2 in for x and 1/3 in for y. I put it into both equations and see if it makes it true, because that's what solutions do. And in this case it does. So this ordered pair 1/2, 1/3 is a solution to the system because it's a solution to both equations. So this is a very nice method. Now this next example, I look at that, in the first example I looked at it and said, hey, I got the y's were additive inverses of each other. That would be automatically a trigger to use that method. But this one doesn't. I got 5x and negative 3x. They're not additive inverses of each other. 4y and 8y, they're not additive inverses of each other, and the numbers are going to be the numbers. But we can use another principle, right, that we use for solving equations. We're just kind of taking it another way to say, I can use the addition principle to do elimination, but I can also use a multiplication principle, which tells me I can multiply both sides by anything I want, and I end up with a new equation that is equivalent. In other words, it has all the same solutions. So what they're doing here is say, maybe we could manipulate this equation 1 so that this 4y turns into the additive inverse of 8y, which would be make it a negative 8y. Well, what would I have to do to take 4y and make it a negative 8y? I'd have to take it times negative 2. Well, multiplication principle and the sides of an equal sign are like grouping symbols, and you have to distribute. I can't just take 2 times that. I have to take 2 times this, negative 2 times this entire side, and then I also have to take it times this side. And that's what they do here. Negative 2 times 5x is a negative 10x, plus a negative 2 times 4y is a negative 8y, and they just leave it as a subtraction. And then I have to take negative 2 times 22, and I get a negative 44. Nice, that following the rules. This is an equivalent equation. All the solutions to this equation are exactly the same as the solutions to this equation, because I just used the multiplication principle and I did it correctly, right? Well, now I have additive inverses here. This will add up to 0. So if I add this side of this thing, again, if you want to picture it, it'd be like I have 3 of these same size weights that are x amount of weight, and then I have 8 of these bigger weights or smaller weights or different size weights that are 8y's, right? And on the other side of the balance scale, I got 18 pounds. Now it's a little different with that negative, but you're going, that's the visualization I have. If I take all those weights on the left side of that balance scale and I add it to this side of this thing, well, that's fine as long as I take that 18-pound weight and put it on the other side of the balance scale with this one. In other words, I'm adding the same weight to both sides. That's the addition principle. So after we manipulate our equation so it'll have the purpose we have in mind to eliminate one of the variables, then I can add these together. And this up and down addition is a very nice way to do your work. Is when I add these two I get 0. That would be what I'd look at first. First I got to make sure that it's going to have the purpose that I have in mind to get this equation to have just one variable. And then negative 10x plus negative 3x is a negative 13x. This again is 0. Negative 44 plus 18 is a negative 26. They solve this equation, they get x equals 2. So there's one part of my ordered pair for the solution. So then I take this and then I use substitution again. And we've done that before. Going way back to the first part of graphing, they graphed by using substitution. You take some value for x, put it in there, and see what y would have to be to make that equation true. Well, now we have a specific value for x that we want to use, which is 2. And they use equation 2 in this scenario. You can do either one. Usually I'm looking for things that are easier. I'll take a little look at that and try to think the steps through a little bit before I decide which equation to use. Mostly that looking for something that the math will work out easier. But they use equation 2 and they put 2 in here. I get a negative 3 times 2 plus 8y equals 18. You get negative 6 plus 8y equals 18. Now I have another equation again with just one variable, right? So I can solve that for y and I get y equals 3. So according to my elimination, or the addition principle I applied, after I did multiplication principle to make sure the addition principle is going to have the outcome that I prefer, which is that I eliminate one of the variables, then I substitute in, I get my other value for my ordered pair, and I end up with this ordered pair 2, 3. And they even tell you again what that means. It means x is equal to 2 and y is equal to 3. And then how would you confirm that that really is a solution? I would go back to the originals, and they don't show the check work here. But for this to truly be a solution, the way I check that is put it into each equation and see if it makes it true. So here's basically another step to prep the equations and then use the elimination method. Example 6. Now here we have a scenario where there's no real true multiples. The other one had I could multiply multiple of 4y to get it equal to the additive inverse of 8y is just a pretty simple multiple deal. Here's a case where I may need to manipulate both equations to create a situation where I have additive inverses in the terms. So I have 2x plus 3y equals 17 and 5x plus 7y equals 29. Well, it's your decision. I could use the 3 and 7y's here, right? And what would be a common multiple of 3y and 7y, which would be 21y? And hey, maybe I can make one equal to negative 21 and the other one equal to 21. That would work. But in this case, they use 2 and 5, and that would be my choice too, just because the numbers end up. What I'm looking for is a common multiple of 2 and 5. Well, that's 10. So I could, make this equal to 10x, and I could make this equal to a negative 10x too. And then I'd have additive inverses, and then when I use the elimination method or use the addition principle, really, I eliminate a variable. So what they do is they manipulate both equations. This one they decided to multiply both sides by 5. You have to distribute, and they end up with 10x plus 15y equals 85. Do you think knowing and really getting real comfortable with the distributive property is important? Yes, definitely. I mean, if you're still struggling with understanding what that is, it will eat you up on this kind of things, because here we're using it just to set up our equations to be in the right form. We're using the distributive property twice. And a whole bunch of problem solving to figure out what to multiply by. So they end up with this equivalent equation of 10x plus 15y equals, and then I also have to take 5 times the other side, which is 85. Well, if I just left that, I just manipulate that and I said, well, 10x and 5x are not additive inverses of each other. I need to manipulate this one too and multiply both sides, in this case by -2. Remember that I need to get one of these variable portions or terms to be additive inverses of each other. So this one they multiply by -2, and which gives us -10x, and then I have to distribute. I get a -14y plus a -58. Well, now when I add these sides together, I end up with 0 for the x's, right? These are additive inverses, and I end up with y, which is nice that it fell out that way. And basically, just after adding, I have it solved for y, which is y is equal to 27. Now, before we were finding the x first, right? Like I said, it doesn't necessarily have to be that way. Now I have one of the numbers of my ordered pair. I have x, and then the second coordinate is 27. We just figured that out. So I need to figure out what x will be. Now I go back to substitution. I put 27 in for y, and now I have an equation with one variable again, just like I did here. But once I have a variable or an equation with one variable, I can solve for that variable, and in this case I get -32. So what I think I have found is the ordered pair for the solution to this system is -32, 27. Right here is the ordered pair. Well, then I check. I plug those two values in for their variables in each equation, check, and see if it makes it true. In this case it does. There's another kind of scenario that happens. We talked about it last time with substitution. If I end up with parallel lines, there is no solution. The other scenario that can happen, and this works the same way with substitution. I'm going to tell you that if you decide either one of these methods and you end up with something like what we're going to go through happens, it indicates that these two lines are actually the same line, or they're the same ordered pair solutions just laying over the top of each other. In other words, there's an infinity of solutions. So let's go through this one, and I probably wouldn't recognize this right away, but when I'm going to use elimination method, and usually when it's in standard form like this, which means the x and the y are on the same side of the equal signs, that's probably going to be the easiest method to use, is elimination. When it's solved for some variable, then that's maybe the best thing to do is substitution. But let's look at this right now. Well, what they do is they say, well, I have a -12y. I could take 4 times 3y, and that would be 12y. It would be the additive inverse of 12y. So their strategy is to manipulate equation 1 here and take 4 times both sides, and that's what they illustrate here in red. And hey, I got this. This is nice. This is what my plan was. I was going to eliminate the y. Well, they do this, and make sure you distribute. They end up with this new equivalent equation of 12y minus 8x equals 24, and which is the equivalent equation. The multiplication did distributed correctly, and so on. Well, when I add these two things together, I end up, hey, these go to 0, but also the x's go to, these are additive inverses of each other, and in this case these are additive inverses of each other. We end up with 0 equals 0, which means that no matter what variables you put in for y, it will work for both of these at the same time. Or what I just described is this graph right here, that they lay right over the top of each other. So when we end up with no variables left, and it actually is a true equation where 0 is equal to 0, in this case it is true. It means it doesn't matter what variables you put in for, or what values you put in for the ordered pairs, making sure that you have to have that relationship maintained. Doesn't matter which equation you start to try to find it. Like if I put 0 in for x right here, if I put 0 in for x in this one to find the y-intercept, right, I'd get 3y equals 6. Solve that, you get 0, 2. The y value is 2. Well, if I put that one in here, I'd get 0, 2, and so on. And I could do that. And if I was in a real high stakes test, like the chapter test or something like that, and I forgot what this means, try some ordered pairs. If I can do multiple ordered pairs and actually have them work in both of these things, that means that there's an infinity of solutions. In other words, we have to do set builder notation for infinity. Because we're not really graphing these things. So I say it's a set of all ordered pairs x and y such that 3y minus 2x equals 6. Well, they picked one of the equations and they say, and basically any ordered pairs that work in this one work in the system, or they're also solutions to the system. Now I could write it this way too, just use the other equation because it's true both ways. This is a set of all ordered pairs x, y such that a negative 12y plus 8x equals negative 24. So every ordered pair that works in this equation, is a solution to the system. So then they have rules for special cases. One of the things if I had this, when we did that, when I was talking about it, I probably would go right here. I might not notice that. But if I solve both of these equations for the slope-intercept form, and I basically said solve this for y, and I solve this one for y, guess what? You're going to end up with the same equation. You're going to have the same slope with the same y-intercept. Isn't that true here? Here's my y-intercept, and the slope is looks like 2 over 3, or 2/3, right? And they would both end up being exactly the same equation. The other one we went through, and I talked about it in the other substitution deal, when I have things in slope-intercept form, if I have the same slope and different y-intercepts, that means that I have parallel lines. In other words, there will not be any solutions. Well, here they define that without having to go to the graphical sense to that, though. I think thinking and being able to visualize these things will save you a lot of time if you can see that. So when I look at two lines and I say, hey, these are parallel, I don't have to do substitution. I don't have to try to do elimination if I think that's the thing to do. I know that there's no solution to this system because they never intersect. But when we get this thing here, that's what they're talking about. Is if you obtain an identity such as 0 equals 0, then the system has an infinite number of solutions. The equations are dependent, and which means that they really lay completely over each other in a graphical sense. Since the solutions exist, it is consistent, meaning that these are words that are from the end of section 1. We have a dependency and a consistent, which consistent means that there's at least one solution. In this case, there's an infinity of solutions. The other case is we can have for these special cases is we obtain a contradiction or a not true statement, like 0 equals 7. Then the system has no solution, and it means the system is inconsistent. No solutions. It is not dependent. Okay, so it's independent and no solution. Another way to say this graphically is they are parallel lines. They never intersect, and they're not the same line, or they don't intersect at one point. Well, they could say the third one here, the third case, to just take the word special out of here. The third case is they intersect at one point, and that's usually in applications we're kind of hoping that happens, because that is usually some kind of specific indicator of where we should go with our business, if it's a business modeling application or cost of production stuff or whatever. There's a lot of different things that make themselves available to us when we have this new set of tools called systems. Excuse me. Now just this last part, it says when decimals or fractions appear, it often helps to clear before solving. This is a strategy again, and I definitely, when it has to do with the elimination method, it is really hard to find LCMs between fractions. How can I make 2/10, which is a decimal right here, is 2/10? How do I make tenths into something that is the opposite of 1/7? Those are really hard to work with multiples. We're used to working with whole numbers. Well, I can use a strategy that we had before about just saying, wouldn't it be nice if we didn't have these fractions here? Well, I can use the multiplication principle, and I can make equivalent equations to these fractional equations and make my setup for elimination a lot easier. So that's what they're doing here. It says, why don't we clear these decimals first? And really this is 2/10 x, 3/10 y, and 17/10 if I wanted to think about them as fraction. Well, what would you multiply to get rid of tenths? You take 10 times both sides. And that's what they do here. They multiply both sides by 10. And how you get rid of decimals is it is always a multiple of 10, which could be 10, 100, depending on how many digits are the right of the decimal. But they get a new equivalent equation of 2x plus 3y equals 17. We use the multiplication principle. I know that the solutions to this one right here and this one are the same. Well, this one I have 7ths, 5ths, and 35ths. Well, I look for an LCM of the denominators, and which is going to be 35. So if I multiply both sides by 35, I'm going to end up with an equivalent equation that has no fractions. And it ends up being 5x plus 7y equals 29. Now I would hope by this time that, when you take 35 times 1/7, there shouldn't be any need to pull out a calculator. It's going to be 35 is really 5 times 7, right? So I can write that times 1/7 as 5 times 7 over 7 times x, which is 5x. Remember how to pre-simplify when you're multiplying. If that's still cloudy, boy, I recommend that you get real clear on that and the other things to do that, because they don't go through all that anymore. They're expecting you to know how to do that math. So now I have these two new equivalent equations. I can use elimination, which is, I would guess, would be something that basically they already gave us these two equations or something similar to that. It would be, we'd want these to be 10x and negative 10x or something like that. So I can use the multiplication principle again. But why eliminate fractions was now I can see how to create additive inverses of each other and use what my goal in using the elimination method is to eliminate one of the variables so I can get a value for that. Okay. So here is a summary of both methods again. To solve a system using substitution, you want to isolate a variable. I would say solve for a variable, unless it's already isolated. If it's in slope-intercept form, it's y equals some number times x plus some number, right? Set up really well already for substitution. Then you substitute for that variable in the other equation using your parentheses. Okay, so you put it in there. Now you're going to have an algebraic expression in for a variable. To solve the equation with substitution, in which substitution was made, you're going to end up with an actual numeric value for one of your variables, and then you substitute it again into one of the original equations to find your ordered pair, right? And that's what they're describing here. Very good thing to look through, make sure you understand that if I use that. And here are the steps to solve a system using elimination, is write both equations in standard form. And I could show you some cases where that's not absolutely true all the time, but usually that's a better way. You multiply both sides of one or both equations by a constant if necessary, so the coefficients of one of the variables are opposites. I use the word additive inverses. Remember, I've said this many times, that there's three things that mean exactly the same thing: opposites, additive inverse, or -1 times something creates this scenario. So if I have 6, I can take -1 times I get -6. Hey, they're opposites of each other. Also, they're called additive inverses because when you add those together, you get 0, and then you just have that. Good thing to remember about negatives are because there's times when it's just good to treat it as -1 times that thing. So they're telling us we want to set up this additive inverses for one of the variables, and then we add the left sides and the right sides of resulting equations. So in fact, we actually eliminate one of these variables, right? Then we solve for the remaining variable, and now I have a value for x or y depending on which way it went. I substitute that back into one of the original equations, and I can get the value for the other variable, and now I have an ordered pair. And then you check to make sure that they work in the originals, to make sure I didn't make a math error or a principal error if I didn't distribute and basically multiply both sides, the entire side, by whatever I'm multiplying, so on. So here's kind of connecting the concept. We've gone through 3 different methods to work with systems of equations. One was graphical, and it says the strength are it gives you a nice picture of what's going on. In fact, they probably in most cases will give a graphical, but its weakness is that it only will give you, when it doesn't fall right on the grid lines of your graph paper, you can only get kind of an estimate about what the exact values where that intersection may be, if that's what occurs in this system. So, and you'd end up in a scenario where you'd have to say, like, I have 35ths in that one thing. I'd have to draw a graph paper that every grid line would be 1/35th to address the need to be accurate with that, and it gets to be not practical. So we have 2 other methods that are giving us exact solutions. That's what we're looking for most of the time. So it does yield, that's the strength, is it yields exact solutions. It's easy to use when a variable has a coefficient of 1. In other words, we may have solved for one of those variables because we had like 2x plus y equals 3. Hey, that variable has a coefficient of 1. That's what they mean. They say, hey, with one step I can solve this for y. This might be a good substitution strategy. The weaknesses are this, and they're both elimination and substitution can be this way. It introduces extensive computations with fractions when solving more complicated systems. And, we could use some strategies to deal with that up front, but usually we don't, and the solutions are not displayed graphically. That it can be a weakness because you may not understand or you might not catch. This is where I see a lot of student errors, is that you get a scenario where it's the 2 lines are laying over the top of each other. They use elimination or substitution, you end up with like 2 equals 2. The variables are gone and you're going like, now what? Well, if you end up with a true situation with constants, they call it an identity situation. It's telling us that everything, no matter what you put in for ordered pairs in either one of these equations, are going to be the same for both. In other words, the lines are overlapping each other, so the graphical part of that's nice to be able to visualize. And you're going to say, hey, it's an infinity of solutions. Well, if it doesn't, if you come out with something where they do not equal each other, so I end up with something like 1 equals 2, which is obviously not true, I end up with a false situation coming out with constants. That indicates that there are no solutions. In other words, I have parallel lines. And that part of it is, I see a lot of errors around that because you do not necessarily have a visual of what's going on. You can do that if you want. In fact, I recommend that, but go back to that graphical stuff. It gives you a picture of what's going on. All word problems, they should say all problems. If you can draw a picture of it, you should, right? So draw a picture. Though I do know these things and these types of problems can take a lot of time. And that's a weakness. You have a lot of computation. A lot of steps can happen. Not more complicated things. Not like all of a sudden we're trying to design a rocket here or say that it's rocket science. We're applying simple steps, simple things that we've already covered many times in algebra. We just need to understand why we're, where we're going, where we start and where we're going, and how can I apply these principles and properties to make this happen. Well, the elimination method we just went through yields exact solutions, which is very favorable. It's a big strength. It's easy to use when fractions and decimals appear in the system. And what the strategy was to get rid of those, right? So and that's part of their method. You could actually do it before your substitution stuff, but not always recommended. And then also it says you don't really get a graphical solution. This is probably one area, it's kind of usually what we go through math or what we did in chapter 3 in graphing is kind of showed us one way, then they showed us another way, and then they showed us another way, and then really the preferred method is the last method that they show us in the chapter. There are times substitution is a lot better method than elimination and vice versa. So when you're practicing these things together, you should ask yourself, is this really the best method to try to do this? It is not a good strategy to say, I'm just going to learn this one method and do that well and I'll forget about the other one, because you're going to put yourself at risk in making more errors, because you're going to get yourself in, you might be taking 5 or 10 more steps to get to the solution than another student that chooses the other method. So let's look at these exercises that they start with, and I kind of like that they threw some examples in before they just actually got into the homework, because I want to just talk about what do you think is the best method here, especially like number 2. Would I use substitution here or elimination? And I'd look at this and say, hey, these y's are additive inverses of each other right now. I'm going to use elimination. I can add these together. I know that I'm going to end up with x equals 18. Right there. I'm done. I already have one part of my, not done, but I have part of my ordered pair. I can actually do in my head by choosing the right method. Now I could solve this for y and say that this is y equals negative x plus 10, and then put in here negative x plus 10, and for y I could use substitution, and you're going to get, and if you do all your math right and you apply your principles and properties correctly, you're going to get x equals 18. But you're going to take a lot more steps to get there. So this one right here, let's look at number 8. X equals 2 minus y, and then I have 3x plus 3y equals 6. The best method here is substitution. It's already solved for one variable. So I can take and replace this x and this 3 times x to 3 times the quantity 2 minus y plus this 3y. What's my goal here first? Do I have now an equation with one variable? Yeah, I just have y in there. I can solve for y. This one right here, I would look at this, and I like this form. I could graph this real easily. I could say, hey, I got a slope of 1/2 and it crosses the y-axis at 1. And then I'd go up 1 to the right 2. I'd have my next point. This one has a slope of 2 and it crosses the y-axis at -5. I could graph these pretty easily. Well, what's the best method to get exact? Now I could add these together in a way that maybe I could make, I could take a -4 times both sides, right? And that would make that a -2x. And this is 2. Hey, they're additive inverses of each other. I can do that. But this is a good scenario because it is already solved for one variable. I'd use substitution. In fact, I could substitute this y with this, what this is equal to for y, right? So I could create a new equation, 1/2 x plus 1 for this right here equals 2x minus 5. That would be definitely the best to do that. Same thing here, I'd use substitution, elimination right here. Notice these are additive inverses. I would still use elimination here, even though there's no additive inverses. I would manipulate one or both of these equations. You'd have to be both, right? And I could get rid of the x's or the y's, up to your choice. And I really would say that it's not, it's really your choice. In this case, we got 2 primes. This one, if I want to get a common multiple, is 6. But this one's 10. That's not much more complicated. And so on, you could do either one. So that's section 2. And one more section to go, and then we're going to be reviewing and getting ready for the quiz and the chapter test.